Welcome back, everyone. Ready for another deep dive?
Always.
Awesome. Today, we're going to tackle something that's, well, kind of a big deal. Gravitational field strength.
Yeah, I mean, we literally deal with it every second of every day, right?
Exactly. But
Right.
even though it's always there, there's a lot about it that's kind of mind-blowing, at least to me.
Oh, absolutely. It's one of those concepts that just gets more and more fascinating the deeper you go.
So true. And speaking of going deep, we've got some incredible material to guide us today from open educational resources / open source physics at Singapore.
Really great website. I love how they use interactive simulations to illustrate complex physics concepts.
Yeah, those simulations are going to be super helpful as we try to wrap our heads around this whole gravitational field strength thing.
Way better than just staring at equations on a page, right?
Right. Okay, so before we get lost in space, maybe we should start with the basics. When we say gravitational field strength, what are we actually talking about?
Well, you can think of it this way. Imagine Earth as this giant magnet.
Okay, I'm with you.
But instead of attracting metal, it's pulling on everything with mass, you, me, our phones, everything.
Yeah.
That pull is what we call the gravitational field. It's like an invisible force field surrounding the Earth.
Okay, an invisible force field. So is the gravitational field strength basically how strong that pull is?
Exactly. It tells you how strongly Earth's gravity is pulling on objects at a specific location.
Got it. So does every point in space around Earth have its own gravitational field strength then?
Exactly. And we represent that strength with the symbol G.
Okay, so G is like a measure of how much pull there is at a particular spot.
Right. And the units we use to measure G are newtons per kilogram, which, tells us how much force the gravitational field is exerting for every kilogram of mass.
Newtons per kilogram and code G. Got it.
But here's where it gets a little more interesting.
Yeah.
G can also be expressed as meters per second squared.
Hold on. Meters per second squared. Isn't that the unit for acceleration?
Bingo. And that means that G isn't just about the strength of the pull, it's also about how quickly objects are being pulled towards the center of the Earth.
Whoa. Okay, so the higher the G, the faster something will fall.
Exactly. And that's why, in a vacuum where there's no air resistance, a feather and a bowling ball would actually fall at the same rate.
Wait, really? They'd hit the ground at the same time?
Yep. Because they both experience the same acceleration due to gravity, regardless of their mass.
Wow, that's mind-blowing. Okay, so we've got this invisible force field, this acceleration. It's a lot to visualize.
It is. And it gets even more complex when you start thinking about how to actually calculate these forces.
Yeah, I was just going to ask about that. I mean, if every single atom is pulling on every other atom, how do physicists even begin to make sense of all that?
That's where the concept of a point mass comes in.
Oh, Moss.
It's basically a simplification. Like, imagine trying to calculate the gravitational forces between every single atom in two separate objects.
Yeah.
It would be a computational nightmare.
Yeah, I can't even imagine. So what do they do instead?
They use this idea of a point mass, where they pretend all the mass of an object is concentrated at a single point.
So it's like they're shrinking the whole object down to a tiny dot.
Pretty much.
Yeah.
It's obviously a simplification, but it makes the math a lot more manageable.
Okay, I can see how that would be helpful, but does it actually work? I mean, is it accurate enough?
It really depends on the situation.
Right.
But for most purposes, especially when you're dealing with objects that are relatively small compared to the distances between them, it's a surprisingly good approximation.
Makes sense. So we've got our invisible force field, we've got acceleration, we've got these point masses. How do we actually calculate this G, this gravitational field strength? I'm guessing there's an equation for that, right?
Of course there is. It all starts with Newton's law of universal gravitation, which basically says that every object with mass attracts every other object with mass. And the strength of that attraction depends on, well, the mass of the objects and the distance between them.
Yeah, I vaguely remember that equation from physics class. Something like F equals G times M1 times M2 all over R squared.
You got it. Where F is the force of gravity, G is the universal gravitational constant. M1 and M2 are the masses of the two objects, and R is the distance between their centers.
Right. But how do we get from that to the gravitational field strength, G?
Well, remember that G is the force of gravity per unit mass. So we can also write that as F equals mg, where m is the mass of the object experiencing the gravitational force.
Okay, so we've got two different ways to express force.
Exactly. And now comes the fun part. We can set those two equations equal to each other. So we get G times M1 times M2 over R squared equals mg.
Okay, I see where you're going with this.
From there, we can just do a little algebraic magic, rearrange the terms, and we end up with G equals gm over r squared.
There it is, our equation for gravitational field strength. So G is that universal constant, m is the mass of, like, the Earth in this case, and r is the distance from the center of the Earth to the point where we're measuring G.
You got it. And what's really cool about this equation is that it shows us exactly how gravity gets weaker as we move away from a massive object.
Right, so it's not just weaker in general, it follows a specific pattern.
Exactly. And that pattern is the inverse square law.
Ah, the famous inverse square law. So that's why we keep hearing about that in physics.
It pops up everywhere. And in this case, it means that g decreases with the square of the distance. So if you double your distance from the Earth, the pull of gravity on you becomes 4 times weaker, not just twice as weak.
Wow, okay, so distance plays a huge role here. And I also remember from the source material that G isn't just a number, it's a vector, which means it has both magnitude and direction.
You're right. We've been talking about the magnitude, which is the strength of the pull, but the direction matters too.
So which way does it point?
Always towards the center of the mass that's creating the gravitational field. In this case, towards the center of the Earth.
Okay, so it's like a constant tug, pulling everything inwards.
Exactly. And that brings us back to those astronauts floating around in space. Even though they look weightless, they're still within Earth's gravitational field, right?
Right, so it's not like gravity just suddenly stops working once you leave the atmosphere.
Nope. They're actually in a constant state of free fall. Gravity is still pulling on them, but it's just much weaker at that distance.
So they're basically just falling forever. That's pretty trippy when you think about it.
It is. And that pull, even though it's weaker, is what keeps them in orbit around the Earth.
Okay, my mind is officially blown. So G is telling us how strong the pull is, which way it's pointing. Is there anything else we need to know about how it behaves?
Well, one thing that often trips people up is the idea of positive and negative values for G.
Yeah, I noticed that in the website too. They mention it depends on which side of the mass you're on. I'm a little confused about that.
It's all about that direction aspect we were just talking about. So, like, imagine you have a mass in the center, and you're measuring G on either side of it.
Okay, got it.
The magnitude of G is always positive, telling us the strength of the pull.
Right, the strength is always positive.
But the direction matters too.
Mm-hmm.
So they use positive or negative signs to indicate which way the force is pointing.
So if I'm on one side of the mass and G is negative, it means it's pulling me towards the other side.
Exactly. It's just a convention to represent the direction of the force. They're using a standard coordinate system where, like, if you're on the right side of the mass, the pull is towards the left and vice versa.
Okay, that makes sense. So the sign is just telling us which way it's pointing, but the important thing is that it's always directed towards the center of the mass.
You got it. That's the key takeaway here.
This is starting to make a lot more sense now. We've got the inverse square law telling us how the strength changes with distance, and we've got this positive-negative convention to represent the direction. What else is there to know about how G behaves out in the universe?
Well, there's one really important point they highlight, which is that G is independent of the test mass.
Test mass, what's that?
It's just a fancy way of saying the object that's experiencing the gravitational force. It's the m in our equation, F equals mg.
Oh, right. So what you're saying is it doesn't matter how massive the object is, the gravitational field strength, that G value, will be the same at that particular point in space.
Exactly. It's kind of wild when you think about it. If you were to, like, magically teleport a feather and a bowling ball to the same point in space above the Earth,
Okay, I'm picturing it.
they'd both experience the exact same gravitational field strength.
Yeah.
Because if you look back at our equation, G equals gm over r, squared the mass of that object, that little m doesn't even appear in the equation.
Whoa, okay. So it doesn't matter what you put there, the field strength is determined by the big mass, the m, like the Earth, and the distance from its center.
You got it. The mass of the object only affects the force of gravity acting on it, but not the strength of the gravitational field itself.
So the field is like this constant background presence, and then the mass of the object just determines how strongly it's affected by that presence.
That's a great way to think about it.
Cool. And I noticed they call it an inverse square law field. I mean, we talked about the inverse square law, but what do they mean by calling the whole field an inverse square law field?
They're basically emphasizing that this isn't just some random quirk, this inverse square relationship. It's a fundamental characteristic of how gravitational fields behave.
Okay, so it's like their defining feature.
Exactly. The strength of the field, that G value, always decreases with the square of the distance from the source mass. That's why they call it an inverse square law field.
Makes sense. And they also point out that the G field always points towards the source mass. I guess that's just reiterating what we were talking about before, that no matter where you are, the pull is always directed towards the center.
Right. It's that constant tug drawing everything in.
I'm kind of picturing these invisible lines of force extending out from every object with mass now.
And that's exactly how physicists often represent gravitational fields. We use these imaginary lines, called field lines, to show the direction and strength of the gravitational force at different points in space.
So the closer the lines are together, the stronger the field. Like near the surface of the Earth, those lines would be super dense because G is stronger there, right?
You got it. And as you move further away, the lines would spread out, showing that the field is weakening.
I love that visual. Okay, I feel like we've covered a lot of ground here. We've got a good definition of gravitational field strength. We understand how it's calculated, and we've explored how it changes with distance and direction. What else do we need to know to really master this concept?
Well, one thing that the website kind of touches on is that even though an astronaut in space might feel weightless, they're still experiencing the Earth's gravitational field.
Oh, yeah, they even have that whole inquiry section where they ask students to think about whether the astronaut's conclusion about not experiencing gravity is correct.
It is a common misconception, but it really highlights how important it is to understand the difference between weight and mass.
Okay, so remind me, what's the difference again?
Well, mass is like an intrinsic property of an object, right? It's how much matter it contains.
Okay.
But weight is the force of gravity acting on an object's mass.
So even though the astronaut's mass hasn't changed, their weight is way lower in space because the gravitational force is weaker?
Exactly. That's it.
Yeah.
And this is where this whole concept of G is so important. The astronaut's weight is essentially their mass multiplied by the local value of G.
Right.
And in orbit, that G is way smaller than it is on Earth's surface.
Right.
So their weight is reduced.
That's why they feel like they're floating. It's all about the relative strength of that gravitational field.
It's a powerful illustration of how this G really shapes our experience of gravity.
This is so cool. We've gone from basic definitions to like astronauts in orbit, all thanks to this website and their awesome simulation.
It's a testament to how powerful these tools can be for really understanding complex scientific concepts.
Totally agree. And speaking of the simulation, they mentioned a specific activity for students to try.
Yeah, they challenged them to come up with a mathematically valid equation to actually represent G.
Oh, cool. So it's like a puzzle.
Exactly. Using the simulation, they can kind of test out different formulas.
I like that.
And they even give them a hint, like try typing in expressions like 6.67 times 100 divided by r squared and negative 6.67 times 100 divided by r squared.
Right.
Just to see how those expressions match up with the simulation's results.
Okay, that's a really cool way to like lead them to that equation that we derived earlier, but it's so much more engaging if they can figure it out for themselves.
Oh, for sure. It really turns learning into this process of discovery.
It's like they're saying, here's the sandbox, go play and see what you can build.
Exactly. And you gain such a deeper understanding of the underlying principles that way.
All right, so we've covered what the definition of G, how it's calculated, how it changes with distance, the vector nature of it, the inverse square law field, the fact that it's independent of the test mass, and even how it relates to this whole weightlessness in space.
We've covered a lot.
I feel like I'm finally starting to understand this.
Yeah, me too.
But there is one more thing I wanted to touch on before we wrap up. The website mentions something about using different models to represent G, like linear, quadratic, and inverse square.
Oh, yeah.
What's that all about?
Well, they're referring to different mathematical relationships that could potentially describe how G changes with distance.
So like a linear relationship would mean that what, like G decreases at a constant rate as you move away.
Yeah, exactly. A quadratic relationship would involve G decreasing proportionally to the square of the distance.
Okay.
And so on.
And they're encouraging the students to like actually use the simulation to test these different models and see which one actually fits the observed data.
Yeah, exactly.
That's really cool.
It's a great way to kind of introduce the concept of model building and scientific inquiry in general.
So it's not just about like memorizing formulas, but actually understanding the process of like how we figure out which formulas actually work in the real world.
That's the heart of science.
I love that. Okay. This has been an awesome deep dive. We've learned so much about this whole gravitational field strength, and I feel like I actually have a much better grasp on how gravity works now in general.
It's such a fundamental force, right? It just shapes the universe as we know it.
And it all comes down to this G, this gravitational field strength that literally just permeates everything around us. It's wild.
It really is. It's this invisible hand that's guiding the planets in their orbits and keeps us, our feet on the ground.
And speaking of amazing things, this simulation, I'm playing with it right now, and it really just hits home how much G decreases as you move away from the object. Like, look at this. At just a few meters away from this 100-kilogram mass, G is already tiny. It really puts into perspective how strong Earth's pull on us is, even though the sun is so much more massive.
That's a great point. And it's exactly why we're orbiting the sun, even though it has a much stronger gravitational pull than Earth. It all comes down to distance.
So basically, we're more affected by the things that are closer to us, at least when it comes to gravity. It's like that saying, the grass is always greener on the other side, except in this case, the gravity is always stronger on the closer side.
That's a great analogy. And honestly, that's true for so many things in life, not just gravity.
Totally. Well, I think we've pretty much explored every nook and cranny of gravitational field strength. We learned how to define it, calculate it, visualize it, even understand its implications for weightlessness in space.
We really covered a lot of ground. But there's always more to learn. I'm sure our listeners are probably thinking up even more questions now.
Speaking of which, it's time for our final thought. Something to really leave our audience pondering as they go about their day. So we've talked about how gravity weakens with distance, but does it ever actually disappear completely?
That is such a good question. Like, is there some point where the gravitational influence of an object just stops?
Mm-hmm.
Or does it extend infinitely outward, just, weaker and weaker and weaker?
It's crazy to think about, right? Like, imagine every object in the universe, from the tiniest grain of sand to, like, the most massive black hole, all connected by this web of gravitational forces.
It really is. It puts things in perspective. Even though it gets weaker with distance, that pull never completely disappears.
Right.
So it's like we're all part of something much, much larger than ourselves.
I love that. No matter how far apart things are, there's still this tiny bit of attraction between them. It's like this invisible thread that connects everything in the cosmos.
And that connection, as faint as it might be at those vast distances, that's actually what shapes, like, the large-scale structure of the universe.
Oh, wow.
It's why galaxies cluster together, why stars orbit around galactic centers. It's why the universe isn't just this random scattering of matter.
So this force that we experience every single day here on Earth, it's actually playing this huge role in, like, the grand scheme of things.
It really highlights how everything is connected, even on a cosmic scale.
Mind-blowing. I think we've officially reached peak mind-blown status for today. We started with this seemingly simple concept, gravitational field strength, and we ended up, like, contemplating the very fabric of the cosmos.
That's what I love about these deep dives, and you never know where they're going to take you.
So true. A huge thank you to the folks at Open Educational Resources / Open Source Physics at Singapore for these incredible resources. I know I'm going to be spending a lot more time playing with that simulation.
It's such a great tool for anyone who wants to, like, really get a hands-on understanding of this stuff.
And to you, our listener, thank you so much for joining us on this gravitational adventure. We hope you learned something new today and maybe even gained a new appreciation for those invisible forces that shape, well, everything.
Until next time, keep exploring and keep asking those big questions.